The 150 volts limit outlined in Article 250.20 of the National Electrical Code is not a subjective determination, but rather a threshold rooted in established electrical safety principles. This limit is based on the inherent danger of electrical shock and the escalating risks associated with higher voltages. Above 150 volts to ground, the likelihood of experiencing severe injury or even a fatal outcome from electrical shock rises substantially. In situations involving a 460 volts alternating current three-phase generator, as in this scenario, the output voltage significantly exceeds the 150 volts threshold. Furthermore, the neutral conductor is not utilized as a circuit conductor, and the system does not employ a delta connection configuration. Consequently, the National Electrical Code does not mandate grounding for this specific generator output. It's crucial to understand that while the National Electrical Code might not explicitly demand grounding under these circumstances, adopting grounding practices remains a prudent safety measure. Grounding serves as a safeguard against various electrical hazards, including short circuits and ground faults, thus contributing to a safer electrical environment. When faced with uncertainty regarding the grounding requirements for a particular electrical system, seeking guidance from a qualified electrician is always recommended. An electrician's expertise can ensure compliance with safety standards and best practices. Let's delve deeper into the reasons why the National Electrical Code establishes this 150 volts threshold and explore the implications for electrical safety. Firstly, consider the human body's response to electrical current. When a person comes into contact with an energized conductor, the severity of the electrical shock depends on several factors, including the voltage level, the amount of current flowing through the body, the path of the current, and the duration of the exposure. At voltages above 150 volts, the current level that can flow through the body becomes sufficient to cause severe physiological effects such as muscle contractions, difficulty breathing, ventricular fibrillation, and even cardiac arrest. Secondly, the National Electrical Code aims to minimize the risk of electrical shock by requiring grounding in certain situations. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protective device, such as a circuit breaker or fuse, and to energize the circuit. This rapid de-energization reduces the duration of the electrical shock and minimizes the potential for injury. Thirdly, the absence of a neutral conductor as a circuit conductor further influences the grounding requirement. In systems where the neutral conductor is used as a circuit conductor, grounding becomes essential to ensure the stability of the voltage and to provide a return path for unbalanced currents. However, in systems where the neutral conductor is not used as a circuit conductor, the need for grounding is less critical from a functional perspective. Fourthly, the delta connection configuration also affects the grounding requirements. Delta-connected systems typically do not have a neutral point that can be directly grounded. Grounding a delta-connected system can create circulating currents and other undesirable effects. Therefore, the National Electrical Code generally does not require grounding for delta-connected systems unless certain conditions are met. Now, let's discuss the benefits of grounding even when it is not explicitly required by the National Electrical Code. Firstly, grounding can provide additional protection against electrical hazards. Even if the overcurrent protective device does not trip immediately, grounding can still help to limit the voltage rise on exposed metal parts, reducing the risk of electric shock. Secondly, grounding can improve the performance of sensitive electronic equipment. Grounding can help to reduce electrical noise and interference, which can affect the operation of electronic devices. Thirdly, grounding can enhance the overall safety of the electrical system. Grounding provides a common reference point for all electrical components, which helps to prevent voltage imbalances and other potential problems. In a specific scenario of a 460 volts alternating current three-phase generator, grounding can offer several advantages. Firstly, it can help to protect against ground faults. The ground fault occurs when an energized conductor comes into contact with a grounded surface, such as the metal frame of the generator or a nearby piece of equipment. Grounding provides a lower impedance path for the fault current to flow back to the source, which helps to trip the overcurrent protective device and to energize the circuit. Secondly, grounding can help to reduce the risk of static electricity buildup. Static electricity can accumulate on the surface of the generator, especially in dry environments. Grounding provides a path for the static electricity to dissipate, preventing potential sparks or discharges that could ignite flammable materials. Thirdly, grounding can improve the reliability of the generator. Grounding helps to stabilize the voltage and frequency of the generator output, which can improve the performance of the equipment connected to the generator. In conclusion, while the National Electrical Code does not mandate grounding for a 460 volts alternating current three-phase generator under the specified conditions, grounding remains a valuable safety measure. It offers enhanced protection against electrical hazards, improves the performance of sensitive equipment, and enhances the overall reliability of the electrical system. Consulting with a qualified electrician is always recommended to determine the most appropriate grounding strategy for a particular application. Furthermore, it's important to consider other relevant factors, such as the specific requirements of the equipment connected to the generator, the environmental conditions, and the potential for human contact with energized parts. A comprehensive assessment of these factors can help to ensure that the electrical system is designed and installed in a safe and reliable manner. Let's expand on the different types of grounding systems and their applications. Firstly, there's the solid grounding system, where the neutral point of the transformer or generator is directly connected to ground. This system provides a low impedance path for fault current, allowing for rapid clearing of ground faults. It is commonly used in industrial and commercial applications where a high level of protection is required. Secondly, we have the impedance grounding system, which uses a resistor or reactor to limit the ground fault current. This system reduces the magnitude of the fault current, minimizing the stress on equipment and reducing the risk of arc flash. It is often used in applications where continuity of service is critical, such as hospitals and data centers. Thirdly, there's the ungrounded system, where the neutral point is not intentionally connected to ground. This system can continue to operate even with a single ground fault, but it requires careful monitoring to detect and clear the fault. It is typically used in applications where a temporary interruption of power is unacceptable, such as critical process industries. In addition to these basic grounding systems, there are also variations and combinations that can be used to meet specific application requirements. For example, a high-resistance grounding system uses a high-value resistor to limit the ground fault current to a very low level. This system provides excellent protection against arc flash and is often used in hazardous locations. Another variation is the corner-grounded delta system, where one corner of the delta winding is connected to ground. This system provides a grounded reference point for the voltage, but it can also create unbalanced voltages during ground faults. When selecting a grounding system, it is important to consider several factors, including the voltage level, the available fault current, the sensitivity of the equipment, and the desired level of protection. A qualified electrician can help to evaluate these factors and recommend the most appropriate grounding system for a particular application. Now let's turn our attention to the practical aspects of grounding. Firstly, grounding conductors must be properly sized to carry the maximum available fault current. The National Electrical Code provides tables that specify the minimum size of grounding conductors based on the size of the overcurrent protective device. Secondly, grounding connections must be made securely and reliably. Loose or corroded connections can increase the impedance of the grounding path, reducing its effectiveness. Thirdly, grounding electrodes must be properly installed to provide a low resistance connection to earth. Common grounding electrodes include ground rods, ground plates, and metal water pipes. The National Electrical Code specifies the minimum requirements for grounding electrodes, including the depth, spacing, and resistance to ground. Fourthly, grounding systems must be regularly inspected and tested to ensure that they are functioning properly. Ground resistance testing can be used to verify the effectiveness of the grounding electrodes. Visual inspections can be used to identify any loose or corroded connections. Furthermore, let's explore some advanced grounding techniques that can be used to improve the performance and reliability of electrical systems. Firstly, equipotential bonding involves connecting all metal parts in an area to a common ground point. This technique minimizes voltage differences between metal parts, reducing the risk of electric shock. Secondly, isolated grounding involves isolating the grounding conductors of sensitive electronic equipment from the building's grounding system. This technique reduces electrical noise and interference, improving the performance of the equipment. Thirdly, surge protection devices can be used to protect equipment from voltage surges caused by lightning or switching events. These devices divert the surge current to ground, preventing it from damaging the equipment. In addition to these techniques, there are also specialized grounding products available, such as grounding mats, grounding straps, and grounding clamps. These products can be used to create effective grounding connections in various applications. When working with electrical systems, it is important to follow all applicable safety procedures and regulations. Always to energize the circuit before working on any electrical components. Use properly insulated tools and equipment. Wear appropriate personal protective equipment such as gloves and safety glasses. And never work alone. In conclusion, grounding is a critical aspect of electrical safety and system performance. By understanding the principles of grounding and implementing proper grounding practices, you can help to protect people from electrical hazards, improve the reliability of electrical equipment, and enhance the overall safety of the electrical system. Remember to consult with a qualified electrician for guidance on grounding requirements and best practices. Lastly, let's consider some common misconceptions about grounding. Firstly, some people believe that grounding is only necessary for high-voltage systems. However, grounding is important for all electrical systems, regardless of voltage level. Even low-voltage systems can pose a significant electrical shock hazard if they are not properly grounded. Secondly, some people believe that grounding is only necessary for metal enclosures. However, grounding is also important for non-metal enclosures, as it can help to prevent static electricity buildup and reduce the risk of electrical noise and interference. Thirdly, some people believe that grounding is a substitute for overcurrent protection. However, grounding and overcurrent protection are both essential for electrical safety. Grounding provides a low impedance path for fault current, while overcurrent protection devices trip the circuit when an overcurrent condition occurs. Both of these measures are necessary to protect people and equipment from electrical hazards. By dispelling these misconceptions and promoting a clear understanding of grounding principles, we can help to ensure that electrical systems are designed, installed, and maintained in a safe and reliable manner.